Hi, in this video we'll be talking about radical functions. Those are root functions, square roots, cube roots, and so on. Now we've discussed this already about how we can always take a root function and rewrite it in exponential form with a fractional exponent. So keep that in mind. Now the root functions, or the radical functions, fall into two major families. We've got the even roots, so the square roots, the fourth roots, the 10th roots, and they all have the same sort of shape of graph. They all look like this. And we actually saw this before in the video about how to graph inverse functions. So that's y equals the nth root of x, where n is even. Okay, so the square root, the fourth root, the 10th root, the billionth root, they all look like that shape. Okay? Now, if n is odd, like we want to talk about the cube root, or something like that, well, actually I need a bit more room here. Our graph would look like this. It actually has a domain that is all real numbers. So I guess we've got the same equation. The only thing that's different is that n is odd. Now please take a moment and draw both of these graphs in the back of your book as graph prototypes. Although we're almost always going to talk about the square root graph, so when n is equal to 2, and so we'll be using this graph a lot whenever we do talk about radical functions. Alright, now that you've drawn it in the back of your book on your graph prototypes page, let's do some graph transformations. So if I take a look at this square root function here, of course I'm going to start with y equals the square root of x. That's my prototype. And once I see that, I notice x is marking the location of the heart of the function. So there we're seeing that in the heart of the function there's a minus 7. Outside the heart there's a multiplier of 3 and an extra term of plus 2. So that multiplier of 3 out front says we're going to vertically stretch by a factor of 3. And the other terms are telling us about shifts. We're going to shift 7 units right and 2 units up. And that's it. There's our recipe. Let's go ahead and draw that. Put on a few of the interesting x and y values. So we're going to start with our basic prototype here. Looks something like that. There's y equals the square root of x. Then we'll do a vertical stretch by a factor of 3. All our y values will get multiplied by 3. And lastly, we'll take the blue graph and shift it over 7 units to the right and 2 units up. So notice that here at the origin for the blue and black graph, that point is included in both the graphs, but then the graph just abruptly ends right there. So when we do our shift, our new abrupt ending point is going to be at the point 7, 2. And there's our graph there. So that's y equals 3 root x minus 7 plus 2. Okay. And if we were to comment on, say, domain and range and that sort of thing, the domain would be all real numbers from 7 to infinity. The range would be all real numbers from 2 to infinity. The intercepts, well, we don't have any. Our graph doesn't cross the y or the x-axis. And for the asymptotes, again, we don't have any. The prototype has no asymptotes at all. So when we transform it, still no asymptotes. All right, let's take a look at another example. We will, on this rare occasion, actually take a look at a cube root function here. So let's write our recipe. And I guess before we do, take a look at the heart of the function. It should be factored before we go any further. So I'll factor out that 2, and I'm left with an x plus 4. That's revealing the true horizontal shift. I'm going to shift 4 units to the left, definitely not 8. 4 units to the left. So we'll start with our prototype, which is the cube root function in this case. Then notice we have this -1 multiplier out front there for outside the heart of our function. So we're going to next reflect the graph about the x-axis. Next, we can see the multiplier of 2 inside the heart of the function. So that tells us to horizontally compress by a factor of 2. And lastly, we have that horizontal shift. So we're going to shift 4 units to the left. It's inside of the heart of the function. It's a horizontal shift. All right, let's draw our graph here. I guess -4 might be an interesting value to put on our scaling. So we'll start with our basic cube root function. If you look back at the graph prototypes that we just drew on the last page, since 3 is an odd number, that's what our prototype looks like. Next, we're going to reflect it about the x-axis. We're going to multiply all the y values by -1, change their sign. Okay. Next, we're going to compress our graph horizontally by a factor of 2. So we're basically going to divide all our x values by 2. All of them are going to have their distance to the y-axis cut in half. That's y equals negative the cube root of 2x. And lastly, we're going to shift that green graph 4 units to the left. So there we've got y equals negative cube root of 2 times x plus 4. And again, we can comment on all the attributes, report all the attributes here. The domain this time is going to be all real numbers. The range will be all real numbers. The y-intercept, well, I guess we can find that pretty easily. Okay. If we take a look and we plug in x equals 0 into whichever version of the function seems best, I think actually the original is nice for that. We see that it's the negative cube root of 8, which is -2. So our y-intercept is going to be at 0, -2. Okay. The x-intercept, we can see from the graph, is at -4, 0, and we've got no asymptotes here. Our original cube root function didn't have any, and the transformations won't create any. They never do. So there we have some examples of how to use graph transformations for radical functions. We'll take a look at some more examples in class. Thank you very much.